Hello friends. So, in the previous lecture we have discussed regarding the recursive DFT. So, we have discussed that if I use the formula of recursive DFT, then we need to calculate for the next window only those samples which are newly available in that particular window, and we need to discard the sample which is not required in the new window. Moreover, we have also discussed the example of recursive DFT, and after that we have discussed the advantages and limitation of recursive DFT, and we have discussed that if I use the recursive DFT, then the important advantage we have, that is the computational requirement reduces. However, at the same time the recursive DFT has the same limitation as the full cycle or half cycle DFT have, that is when decaying DC component is present in the acquired signal, say in case of fault, then the accuracy of phasor estimation, that is not proper. And finally, we have discussed a new phasor estimation algorithm, that is LES technique. Now, let us consider one example of this LES technique. So, to understand this, let us consider a current signal having a fundamental frequency of 50 hertz, and this signal is sampled with a sampling frequency Fs, that is equal to 800 hertz. We wish to calculate the phasor values of DC value, first that is fundamental term, third harmonic, and let us say fifth harmonic from the sampled values, and the given sampled values that is given in this table, and the sample numbers are given here, and for each sample the acquired value, that is also given here, and these values are for 16 samples. So, as for 800 hertz sampling frequency, the number of samples in one cycle, that is 800 by 50. So, that is also 16. Now, we know that the size of matrix X, which is unknown, that depends on the components whose phasor value need to be calculated. So, let us say if I wish to calculate phasor value of fundamental term or third harmonic or fifth harmonic. So, depending upon that, the matrix size of X, that is changed. So, as 3 harmonics are present other than DC component. So, here in earlier case first, third and fifth, these 3 harmonics are there other than DC component. So, we have the value of H, that will be 3 in this case, and the size of matrix X, that is 7 cross 1, in which it contains the DC term I 0, the first fundamental term I 1 cos theta 1 and I 1 sin theta 1, the third harmonic, that is I 3 cos theta 3 and I 3 sin theta 3, and the fifth harmonic term, that is I 5 cos theta 5 and I 5 sin theta 5. So, as I told you, I 0 is the DC value, and I 1, I 3, I 5, these are the peak value of first, third and fifth harmonic component, whereas theta 1, theta 3 and theta 5 are the phase angle of first, third and fifth harmonic component respectively. So, the next step is to decide the value of P, so that that can be used for the calculation of the other matrix. So, when we consider the value of H, that is 3, because we need to calculate first, third and fifth other than DC component. So, the minimum value of P, that is 7 from this equation 2H plus 1. So, 2 into H is 3 plus 1. So, minimum we required 7 samples to estimate the unknown values of fundamental, third harmonic, fifth harmonic and DC term. So, let us consider in the first case, let us consider the case number 1, in which we consider the value of P, that is 7, exactly same as the number of unknowns. So, here these are the 16 samples, and when we use these samples and when we consider P equal to 7, so the window becomes like this. We need to consider sample number 1 to sample number 7, and when we use the value of omega 0, that is 2 pi f 0, that is f 0 is 50 hertz. So, we have omega 0, that is this value, and T s, that is 1 upon 800. So, if we substitute the values of omega 0 and Ts, the matrices of A and B, that can be look like this. So, here in matrix A you can see that this in the first row the components are 1, that is the coefficient of the DC. You have cos omega 0 Ts because this is sample number 1, then you have sin omega 0 Ts and similarly up to sin 5 omega 0 Ts, and then when you increase you take sample number 2, you have the second row, and similarly when you consider the 7th sample you have the coefficients from DC term to the sin 5 omega 0 7 Ts. So, the size of this A matrix, that is 7 by 7. On the other hand, if I consider the B matrix, then B matrix is nothing but it contains your sampled values. So, it starts from I 1 and it goes up to I 7. So, if I consider here I 1 is 14.1 and I 7 is minus 4.4. So, you can see this is 14.1 and this is minus 4.4. So, accordingly you have the matrix B, the size of which, that is 7 cross 1. Now, if I use this relation A x is equal to B, then our unknowns x, that is also 7 because it starts from the DC value, the fundamental term, third harmonic and fifth harmonic. So, here when we use this A x is equal to B and when we want the value of x, then finally if I put the value, you will have the matrix A that looks like this, where I have calculated the value, I put the value of Ts and omega 0 and hence you can have this matrix. You already have the matrix B. So, now you can easily calculate the matrix X. So, when you do that, as I told you, you have to take the pseudo inverse. So, that is the pseudo inverse is nothing but A plus, the size of which is 7 cross 7, that is square matrix, and that is multiplied with the sampled vector. So, if you do that, then you will have the value of x here, this 7 terms, that is this value. So, here you can see that the DC value that comes out to be the 1.7156, the fundamental term, that is this first two term I 1 cos theta 1 plus j I 1 sin theta 1, if you obtain the magnitude and angle, you will get 10.12 at an angle minus 1.9 degree. And similarly, if you see the third harmonic, that is I 3 cos theta 3 plus j I 3 sin theta 3, then you will have the magnitude 3.024 and angle 42.85. And same way for fifth harmonic term, you will have the value 1 angle 86.5 degree. However, if you see, if you compare this value with the actual value of the signal which is given by this, then you can see that the DC value, actual value of DC, that is 2, whereas you obtain 1.71. Similarly, the fundamental term magnitude is 10, actual value you will have 10.12, angle is not there, here you are getting some angle. Similarly, for third harmonic the magnitude is 3.024, you have 3 and the angle is 42, whereas here the angle is pi by 4. And same way for fifth harmonic the magnitude is 1, but the angle, that is pi by 2 actual value, whereas whatever value you obtained, that is 86.5. So, these values are not matching. So, further to get the accurate result of this phasor values of DC fundamental third and fifth harmonics, let us increase the number of samples, that is P. So, as I told you, when we increase the value of P which is greater than 2H plus 1, then your matrix A, that becomes a non-square, and that is why you have to take the pseudo inverse. So, let us consider the P that is equal to 10. So, here now you are going to use your P that varies from the I 1 to I 10, and here in this case if you calculate the size of the matrix A, then that is p cross 2h plus 1. So, here your p samples, that is 10. So, it is 10 and 2h plus 1, that is 7. So, the size of A, that is 10 cross 7. Similarly, the unknown matrix X, its size is remains as it is 7 cross 1, because it is 2h plus 1 cross 1, and the size of B, which is p cross 1. So, p is 10. So, size of B matrix, that becomes 10 cross 1. So, here if you calculate the value of matrix A, you will have the value of matrix A like this, which is 10 cross 7 by putting the omega 0 and t s. The matrix B, you have, that is sampled values, which starts from 14.1 to 10th value, that is minus 5.2. So, you have this value and this value. And now, if you calculate the unknown matrix X, then you can have the value of X, which is pseudo inverse of A, that is A plus 7 cross 10, and B matrix, that is 10 cross 1, that or pre cross 1. So, you have the value of X, that is 7 cross 1. So, whatever value you obtain, you can see that the DC value, that is 1.99, which is again very close to the original actual value 2. You have the fundamental component. If you take magnitude of this an angle, you will have 10.012 angle minus 0.1. So, that is also very close to this, and the third harmonic term, you can see it is 3.002 angle 44.9, which is also close to this, and again you can take the fifth harmonic, value of which, that is 1 angle 89.9, that is also very close to this. Now, let us further increase the value of p. So, now let us consider the value of p, that is 16. So, now we are taking all 16 samples in one cycle from I1 to I16. So, if I consider 16 samples, then the size of this A matrix, that is p cross 2h plus 1. So, now p becomes 16. So, this is 16 cross 7, that is the size of A matrix. The size of X matrix, that remains as it is 7 cross 1, there is no change, whereas the size of B matrix, which is p cross 1. So, it becomes 16 cross 1. So, now let us see what is the value of unknown matrix X. So, here when you calculate the matrix A by putting the value of omega 0 and T s, then you will have this value of A, you will have the B matrix, that is your sample values from I1 to I16, and then you have the unknown matrix X. So, you have finally the unknown matrix X, which is 7 cross 1. So, now you can see the DC value comes out to be 2, which is exactly same as the actual value. The fundamental component, that is this value, which is 10 angle 0, and this is also same as actual value. Similarly, if you consider third harmonic term, then if you take magnitude and angle, you will have 3 angle 45, which is same as actual value. And same way, if you consider fifth harmonic, magnitude and angle 1 angle 90, you will have the same value. So, as we increase the number of samples in a particular window, then the accuracy of the LES in terms of estimation of phasor values of unknowns, that also increases. But as we increase the number of samples, the computational requirement also increases. So, we have to optimize at one particular point, that up to how much accuracy we want by increasing the number of samples. Now, to understand the impact of decaying DC component on LES algorithm, let us consider the signal, current signal. When we acquired the current signal in case of fault, then we know that the waveform of this current signal is distorted, and that signal contains decaying DC component along with several harmonics and fundamental term. So, decaying DC component, that is given by, let us say the equation I of t is equal to I 0 e raised to minus t by tau, where tau is the time constant of decaying DC component. fundamental term I 1 cos omega 0 t plus theta 1 and third harmonic term, that is I 3 cos 3 omega 0 t plus theta 3. So, your I t, that is nothing but the instantaneous value of current which changes with reference to time. I 0, I 1 and I 3 are the magnitudes of DC fundamental and third harmonics, and theta 1 and theta 3 are the phase angle of fundamental and third harmonics respectively. Omega 0 is the fundamental angular frequency of the current signal. Now, if we expand this term using the Taylor series, and if we retain the first two terms neglecting the higher order terms, then we have the modified equation of this I t, that is given by this equation. So, here you can see we have the two terms of DC, that is one is I 0 and another is minus I 0 by tau into t. So, now the size of matrix A, B and X, that becomes like this. So, size of A matrix, that becomes P cross, instead of 2H plus 1 it becomes 2H plus 2, because we have the two terms here for DC value. The size of X, that also now 2H plus 2 cross 1, these two are again unknowns, instead of earlier one DC value unknown, now two DC values are there, and the size of B, that is nothing but the P cross 1, that is as it is. So, if I consider the same signal of current which contains the DC value, fundamental and third harmonic term, then the size of which is given by this, and if you obtain the A matrix, then you can see that here the first row, when you start with sample number 1, n is equal to 1, then in that case this term is already there, but the term available, this is also there, but this term is again newly added, that is T s. Same way, when you increase the number of samples n is equal to 2, then this term is added, and as you go up to P, then this term that is added compared to the earlier one. So, here moreover in matrix X unknown, this term is also now available. So, the number of unknowns, that is more than the earlier one, and the size of matrix A also changes, whereas the size of matrix B remains as it is. So, if we carry out performance analysis of the LES, then the performance of LES is better than the DFT when we consider the errors and noise in the acquired signal. However, to achieve the better accuracy, obviously as I told you, we have to increase the value of P, and that increase is the window size. However, the performance of LES is better than the DFT and cosine filters and recursive DFT, particularly when the decaying DC component is present in the acquired signal. Now, to understand or to compare the performance of this LES technique with DFT and cosine transform, let us consider a current signal I t, which is given by this equation. So, this equation contains DC term, it contains the fundamental component, it contains the third harmonic as well as it contains the fifth harmonic, and this current signal is acquired with a sampling frequency of 800 hertz having fundamental frequency 50 hertz. So, number of samples in a cycle, that is n, that is equal to 16, and that 16 samples are shown here. Now, if I plot this signal, then this signal looks like this. So, you can see that there is a decaying DC term along with some fundamental term and some other harmonics. So, if we obtain or calculate the phasor value of this equation using LES, DFT algorithm and cosine algorithm, then let us say we want to compare with fundamental phasor. So, let us consider the value of k, that is 1. So, in that case the actual value of phasor, that is 10 angle 0, and if I use the DFT algorithm, the phasor value obtained, that is 10.15 at an angle minus 3.38, whereas the cosine term we have the value that is 10.12 at an angle 0.68. But if I use the LES technique, we will have the exactly same value that is we have in case of actual one. Same way, if I calculate the phasor value for third harmonic putting k equal to 3, then we have the value of this phasor for third harmonic, that is 3 angle 45. This is the actual value, and if you compare if you obtain this value using DFT, then you have the value that is 2.96 at an angle 40.92. However, as we have discussed in case of cosine transform, that cosine transform is applicable only for fundamental component. If we want to apply for third and higher order harmonics, then it is not able to calculate the phasor value. So, that is why it is unable to calculate this value. Whereas, if I use the LES algorithm, then the value obtained for third harmonic, you can see that is exactly same as 3 angle 45, that is the actual values. And similarly, if I use or if I calculate the phasor value of fifth harmonic term by putting k is equal to 5, then we have the value that is 1 angle 90 degree. And if I use DFT, then you will have the value that is 0.93 at an angle 82.6 degree, whereas as a usual cosine algorithm is not able to calculate, and LES algorithm you will have the value 1 angle 90 again, which is exactly same as the actual value. So, you can definitely say that whenever we wish to calculate the phasor value for fundamental or third or any other harmonics including DC term, then LES algorithm performs better compared to the DFT algorithm and cosine transform algorithm. The only thing is that the number of samples required by this LES, that is higher than the unknown values. So, as you increase more samples, you will have the better result, which is actually very close to the actual values. So, in this lecture we have discussed initially one example of the LES algorithm, and that example we have discussed by considering three different value of p. So, initially we have considered the value of p, let us say that is 7. So, the number of unknowns, that is same as the 2h plus 1. So, whatever samples you are acquiring, that is 7, and the number of unknowns, that is also 7, and then we have seen that we do not get the required accuracy, means whatever phasor value we obtain, those values are not close to the actual values. Then we have increased the value of p, and let us say we have considered 10, and then we see that the accuracy of the phasor values that improved compared to the p equal to 7, and finally we consider p equal to 16, and in that case we have observed that phasor values of the all the terms which we obtain, that is almost equal to the original actual value. After that we have discussed, when we consider the impact of decaying DC component, then how the LES is performed compared to the other algorithms like DFT and cosine transform, and we observed that LES performs better when decaying DC component is present in the acquired signal compared to the DFT and cosine transform. So, thank you.